Hello, Aditya. How are you?
Hello, can you hear me?
Yes, perfectly
Great, great.
clear. Okay, so here with us is Aditya Siram. He will be our first guest for tonight. It's tonight in Argentina, but around the world, this is our first talk, wherever you are. So Aditya is a Scala developer by day, but writes Haskell, Shen, C, Rust, and ATS by candlelight. So you have candles besides your computer.
I'm a Haskell developer now, but that's an old bio, but thank you. Yes.
Okay, full
Yes.
Haskell. Okay, great. So his talk today will be related to that. It's called what functional programming can learn from static introspection. So typed functional programming is very useful, but often difficult to use. And Aditya will propose a solution, which is to steal static introspection from other languages like Nim and D and use it for type level functional programming. So the floor is all yours, Aditya. You can start sharing whenever you want.
Okay, thank you. I assume you can all see this?
Not yet.
Okay.
Yes.
Great. So I'll just get started. Hello, everybody. I'm in the U.S. in St. Louis, Missouri. So wherever you are in the world, I hope you're staying safe and staying healthy. And thanks for coming. So my talk is called "What FP Can Learn from Static Introspection." So let's start off with, what is static introspection in the first place? So just to get a broad overview, it's the idea of being able to query your code base for all of the static information that it has at that point in time, right? So it's the idea that you can ask at any point in time, what is the type of 1 + 1, and use that information somehow. You can even ask questions like, does the expression 1 + hello world compile? Right? And if it doesn't compile, do this thing. If it does compile, do this other thing, all in the course of your program. You can ask things like, what are the fields of an object? What are the, sort of the keys and the types inside of this record, right? And conditionally generate some runtime code based on the answers to those questions. So as a broad overview, that's what static introspection is. But there's a second piece that's called compile time function evaluation. These two things kind of go together. It's the idea that at compile time and at runtime, you have access to the same language. So let's say that you're in some standard imperative programming language, and at runtime you have for loops and while loops and functions and like assignment and things like this, right? Then you have those same idioms and facilities available to you at compile time. So the compile time language isn't this completely different, like hard to use thing versus the runtime language. They're both the same. And when you put them together, I think you have this potent mix where you can really take advantage of a lot of the static information that you have at any given point in time in a way that you can't really do today in typed functional languages that are sort of the ML tradition. And I'll have more concrete examples coming up. So one of the big advantages of compile time introspection and all this stuff, the one that people talk about the most is performance. So the idea here is that if you can introspect on types and say something like, if this type is an integer and that type is an integer, and you're adding the two, well, do this really specialized fast integer add operation. If it's an int and a float, do this other thing. So at the end of the day, like basically it allows you to sort of play the optimizer. You're taking on the job of the optimizer. And in some cases, you're even taking on the job of sort of the JIT compiler, right? It is definitely a benefit, and the benefits are real. But I'm going to argue that it's not a silver bullet. And even though a lot of the rhetoric around compile time function evaluation centers around performance, it is not the most important benefit, in my personal opinion. More importantly, I think it makes type level and compile time programming just utterly boring. It makes it accessible, it makes it maintainable, and I mean, it makes it possible. And I know the word possible is loaded because you can just come back and say, well, the Haskell type system is Turing complete, so therefore everything is possible and this kind of thing. But I mean, sort of practically possible, like something that you would reach for. And being able to query your type level, being able to query static information, not just type information, at any given point allows you to have library level and I think project specific tooling that has the potential to greatly improve like developer productivity. And again, these are all high level things, but I will have concrete examples coming up. It allows you to have, I think one of the better benefits is it allows you to have customizable compiler feedback. That means you have complete control over error messages based on the types that are being generated at that given point in time. So you can have library level and DSL level user experience. This is extremely important in my opinion. Like being able to just create a DSL is not enough. Having compiler diagnostics that understand the DSL that you just created is as important as being able to create that interpreter or whatever in the first place. So I'm going to show you examples of that as well. And I think not most important, I think one of the big benefits is that if you cut this loose, the static introspection stuff loose on a bigger code base, I think it changes the way you think about system design in a type functional programming language. It encourages this idea of sort of structural looseness, ideas like structural typing and row polymorphism kind of get at this, but aren't really as heterogeneous and introspectable friendly as the kind of stuff that I'm showing you. Typed functional programming is in some ways obsessed with keeping things canonical, right? So there's only one representation of a UUID, there's only one representation of a user ID, this kind of thing. And having global things type classes just sort of mediate just this one thing. But in larger code bases you have sort of this heterogeneity even in types that we need to be able to take advantage of, and I think that this offers some advantages there. So the examples that I'm going to be showing you are in Nim and D. These aren't particularly popular languages, and they're not even functional languages. In fact, they're imperative languages in sort of the C++, Ada, Pascal, Modula, Oberon, Algol tradition, right? So in some ways the farthest thing from functional languages. But I think that the ideas that they have are things that we should be adopting in functional programming languages. So while these are both great languages in their own right, the goal of this talk is not to have you it's not an evangelism talk. It's not go rewrite your systems in D or go adopt D for your next, or go adopt Nim for your next project or your next business or whatever. It's let's take these ideas and put them in the next functional programming language. And all of the examples that I'm going to show you today are real world examples, things that I've encountered myself, that if I had the facilities that I'm going to show you, would have made my life a whole lot easier and would have made the software that I was writing a whole lot better, honestly. So let's just jump in. This is compile time evaluation in Nim. So Nim has this sort of Python-looking surface syntax. This just creates a function called sayHello that takes a string and outputs a string. But the real magic is happening in this when Nim VM line right here. And what that does is it differentiates between what this function will do at compile time versus what this function will do at runtime. So at compile time, it will do this thing. And at runtime, it will do that thing. So inside of a static block, which is a compile time block, if I call sayHello with BuzzConf, it's going to do this. And if I do it outside of the static block, it's going to do that. So what that means is when I compile this program, the compiler spits out hello to BuzzConf at compile time. I haven't even run it yet. This is compiler output. And when I run it, it's going to say hello to BuzzConf at runtime, right? So there's two different behaviors, one at compile time and one at runtime. And you can convince yourself that there's no compile time information being passed into the binary. If I grep at compile time in the binary, there are no matches. If I grep at runtime in the binary, there is a match. So there's this clear separation between compile time and runtime. Compile time information stays at compile time. Runtime information stays at runtime. There's a way to pass information back and forth, but it is an explicit thing that you do, that if you don't do it, that information just doesn't exist at runtime. So you have that assurance. And I also want to get into static introspection. In this case, I'm going to use D as the example. And it's not because Nim can't do any of this stuff. It's because static introspection is something that's front and center in D. It is as central to programming in D as some types are central to programming in ML-like languages, right? It's something that people just reach for. And as far as I know, this is the first language that encourages it to that level. So here's some D code. This is just standard D code, and as you can see, very sort of C, C++ influenced. So I'm creating a struct, which is just like a C or actually a C++ struct. It's got a couple of members. There's an integer member and there's a string member. And here at compile time, I'm asking it to print out all of the members of this struct S. So when I compile this, it's going to print out an int and a string. And this corresponds to an int and a string, right? And you don't just have to print out everything. You can query for a specific thing. So here, I am querying specifically in the struct S for a field named an int. And at compile time, it's going to print out the type of that thing, which is an integer. And if you query for something that doesn't exist, like food, it's going to give you a compile time error message that says that food doesn't exist. So this kind of like, querying for things in your static environment is a safe thing to do, because if you don't do it correctly, you get a compile time error message. This isn't something that just silently fails at runtime. And just to ensure that there's no hanky-panky going on, so this isn't like when you query for like the integers and the strings inside of the struct. It's not just going and running a regular expression on this text. That would be cheating. In fact, it's actually doing something more than that. It's actually querying the environment at hand for the static information. So here, instead of a struct, I have a class. A class inherits more stuff than a struct. So when I print all of the members of a class, it's not just giving me an int and a string. It's also giving me all of the inherited methods that classes have, like toString and toHash and the comparison operator and equals operator and all this stuff. So if you are at all familiar with like typed object-oriented languages, like this should look relatively familiar. These are standard things that come with like classes and objects in most other object-oriented programming languages like Java. But this shows you that this isn't just like parsing over this text and pulling out these things. It's actually doing some kind of semantic analysis, which is important. Now I want to talk a little bit about performance. So one of the biggest touted benefits of compile time function evaluation is sort of this performance aspect, where you can hyper specialize your code to a single operation. And the benefits are there, to be fair. But performance is a fickle beast. Like if you've ever tried to sort of optimize something, that like the answer to every optimization question is it depends. It depends on the hardware. It depends on what kind of hard drive you have. It depends on the processor. It depends on all kinds of stuff. But the benefits, I think, of compile time function evaluation, especially in the context of Nim and D, where you have the same language at the compile time level and at the runtime level, is that these efforts can be measured and they can be ditched. You can walk away from something that didn't quite work out very easily. In a lot of languages, in a lot of functional programming languages, if you move something to compile time, it's a lot of effort. And if it doesn't work out like you thought it would, walking that back is a difficult process. You can't just sort of push that aside and move along because you've already sunk a lot of time into, getting that right in the first place. And Nim and D make it so that you can experiment with this stuff, and if it doesn't work out, at most you've lost a couple of days and you can just move on with your life. And here's an example. So here I have a large-ish CSV file that I'm reading in at compile time using Nim. So it's like 21,000 lines, and I don't know, is that even big anymore? It's not big. It's, I don't know, small to medium, I guess, but it's enough that it takes a non-trivial amount of time to parse through, and if you do it naively, right? So here's a standard here's a function called readCSV that takes a string and outputs all of the row and column data, right? So it's a sequence of strings, which is, rows versus columns. And the code in here is not particularly interesting, except that it is just standard imperative code. There's just a while loop, and you're updating a counter. You're not updating a counter, you're updating a mutable variable. So the standard stuff that you would do in any imperative programming language. So the only way to know that this is actually running at compile time is because this parsed variable has this const modifier. And const means do all this stuff at compile time. You statically read this large CSV file at compile time and then pass it to this function that is available both at compile and at runtime. So when I do that, there is a performance benefit. I'm not going to say there's not. Looking up any row and any column is nearly instant, right? So the 100th row of the 100th column is an instant lookup. But I'm going to argue that even though we have that, in this particular case, it's not always worth it. Because this took 10 seconds to compile. That little 6-line snippet of code took 10 seconds to compile. And it resulted in a 22 megabyte binary. And this is from a 2.4 megabyte CSV file. So all of the metadata associated with sequences and strings and stuff like that Nim adds to all of that data being read in at compile time bloated up the binary to 22 megabytes, even though the actual raw data was only 2.4 megabytes. So we can switch to runtime parsing. And switching is as simple as taking that const and turning it into a let, and taking that static read and turning it into a read file. So now, just with that little change, read CSV is now run at runtime as opposed to compile time. And compile times for that binary went down to under a second, maybe even half a second. And you should expect this because now the compiler is doing less. And compile time processing is much slower than runtime processing. Generating that lookup table is much slower at compile time than it is at runtime. And the size of the binary went from 22 megabytes to 170 kilobytes. Now, there is a little performance loss. The initial startup time of that binary used to be instant, now took a little under a second. But I'm going to argue that backing out was the right call, because if we're reading the CSV in and using it a bunch of times in a long-running program, that initial sub-second startup time is negligible compared to having a 10-second compile time imposed across all of your development team. So in this case, while that seemed like a good idea, backing out, I think, was the right call, and backing out was easy. And that's the point I'm trying to make. Here's another example. We have regular expressions in D, right? So in D's standard regular expression library, there's two ways of parsing a regular expression. One is at runtime, and one is at compile time. So at runtime, you place the regular expression where these dots are with this R. At compile time, you use the CT regex bang template and place it inside of these backticks. That's the only difference. And the idea is that if you use the compile time regular expression, it generates this super specialized, highly efficient, regular expression engines just for that thing that you passed in. So this isn't a general regular expression engine. This is one that's completely specialized to the regex that you are interested in. So in theory, much, much faster. So let's test this. I tested it on this primality tester. If you've never seen this before, it's actually pretty cool. This is a small little regular expression that tests for the primality of a number, right? And the way you do that is, say you wanted to test for if the number 19 was prime, you would pass to this regular expression 19 ones, right? And then it would it would eat up that regular expression in chunks of 2, then chunks of 3, then chunks of 4, then 5, then 6. And if there's a match, it is not prime. If it fails to match, then it is prime. So this is a negative tester. If the regular expression fails, then it is prime. If it doesn't fail, then it is not prime. And as far as I can tell, this is credited to a Perl hacker named Abigail, and I think this little trick is at least 15 years old. But the reason I use it is because it backtracks a lot. It goes all the way to the beginning of the input and has to do that every single time it tests. So I tested this against the 10,000th prime. I found this on Wikipedia. It's 104,729, if that at all interests you. And unfortunately, the performance was not great. Both the specialized compile time regular expression and the runtime regular expression both took about 2.5 minutes. And PCRE was faster than both of those, right? So in this particular case, again, what seemed like a good idea in theory was on the test not working out. But I want to say this is still a benefit. Having compile time evaluation in the way that it works in Nim and D are still benefits because it gives you the ability to just walk away. If something doesn't work out, you just change CT regex bang to R and just kind of move on with your life. In a functional programming language, when you move something to compile time, even if it's just template Haskell, walking away from, even if it's just sort of a macro-based thing, walking away from that is pretty difficult. It's not easy to do, especially if your code base is big. And in this case, in our case, with static introspection, at worst, you've lost a couple of days of work, and you still have this runtime library that works. And if you ever get to a point where that D hyper specialized regular expression engine on one particular regular expression seems to be 5 times faster than the runtime version, then you can selectively enable it for just that. It gives you the ability to experiment and the flexibility to use it when you need to, and not have to take on that cost for everything that you do. The next thing I wanted to talk about is this idea of developer productivity using static introspection, and looking up fast the kind of stuff that you're interested in your type environment and your static environment. So this is an object in Nim. It's no different from a record. In Nim, an object is just a hierarchical record. That's all it is. So it's got these fields, it's got an int field, it's got a sequence of integers, it's got another integer and a string or whatever. And it's got these weird naming conventions. It's got O1 user underscore ID, O1 IDs, and then it switches from, sort of underscore to, sort of camel case here and back to underscore down there. And it doesn't even respect the, the capitalization over there. And the reason I'm showing you this weird looking object is because this is representative of the kind of data that you see in real code bases. When deadlines approach, when you're dealing with legacy code that has been around for a long time, you see this kind of stuff. People don't always clean up after themselves. They don't have time to do that. We have to, just kind of work with what's there and move on. So the idea is that I don't want to have to go look all this stuff up all the time. I just want the computer to tell me what's in there. And in Nim, I can do that just like I did with D and alt members. So I have this function called gather fields that takes a type and outputs sort of this lookup table of field names to types, right? And it uses this built-in called field pairs that just iterates over all the fields and like adds them to a mutable variable at compile time. So when I run this at compile time, right, using gather fields, and I just like print it out to the screen, the compiler prints out all of the field names and all of the types. It prints out the user ID, the IDs, the age, and like the user address and things like that. So I can now take this output and plug it into my editor and get like cheap and easy completion, you know, for that specific type. And it's fast, it's not slow. So you're looking at this, if you are a type functional person, you're looking at this and you're saying big deal. This is not that big of a deal. I have a language REPL, and that REPL is great. Especially if I'm a Haskell programmer, I have GHCI, and :I gives me all I want. So in Haskell, the REPL that comes with GHC is called GHCI, and :I stands for :info, which prints out everything it knows about, you know, an object. So I could just go :info and that object, and it would print out the exact thing that I'm showing you. This is already built in, and it knows how to do this. But how about this? I'm going to say that it's the end of a long day. It's the end of a long week. It's like a Friday, and you know, I'm working late, and I'm kind of bleary-eyed. I'm not really thinking straight anymore. But I know that inside of this object, right, there's some kind of sequence of integers that has some kind of name like IDs. I don't particularly remember that the object field names start with an 01, or whether it's camel case or snake case or what have you. I just happen to know there's some IDs in there, and it's a sequence of integers. So how do I figure this out, right? So I can just use the same thing again. So here I'm using that gather fields function to gather that lookup table, right? And I'm using standard list functions. These are just Nim standard library things that you would use to operate on any sequence, and I'm doing it at compile time. So I'm taking that list and I'm filtering it and looking for all of the keys that have the phrase IDs inside of it and have the type sequence event. And so at compile time, it's going to spit out the thing that I want, 01 IDs and sequence event. I did not have to go look this up in source. I didn't have to go hunt down the source in some module that might be 2 or 3 dependencies away to figure this out. I didn't have to go stop what I'm doing and go read the rendered documentation to figure this out. I wrote a quick and simple query that I can plug into my editor and get the precise information I want without having to like stop what I'm doing and go do something else. And this is kind of what I'm talking about. This is allowing me to improve my productivity by being able to precisely query what I want in the static environment that I'm in right now, right? So this is letting the computer do work for me. It's letting the computer tell me about information that it already has, as opposed to me having to go look it up in some third-party source. So this lets you make domain-specific tooling that fits your project, right? A tiny little tool that does one thing, has one use, and that you throw away afterwards. And the amount of work this would take to get into sort of like big IDE is huge. And an example of this is libclang. Libclang is, if you've heard of Clang, Clang is a C++ compiler. Libclang is the C wrapper around that compiler that provides like completion information and allows you to parse C++ code, and allows you to plug all that stuff into like an IDE. It provides this, tooling for you. But it's huge and it's complicated, and it took a team of people a long time to make it. And with static introspection, I've been able to get a very lightweight version of that without a whole lot of effort. And I think that functional programming languages could use something like this because we don't currently have that. We need to be able to query our static environment. We have a very rich static environment we should be able to query. The other example I wanted to talk about is this idea of data type diffing. So data type diffing is essentially comes down to what fields were added and removed between 2 different versions of a data type. And this becomes hugely important, in my opinion, especially when you start thinking about things like serialization, right? So if you've serialized a data structure at some point in the past, and the data type has moved on in the future, how do you get from this version to this version? Right now, this is a hugely tedious question to answer because it involves a lot of like manual looking up of what the thing used to look like and what it looks like now. And we should be able to use a computer to do that for us. So here's two different versions of the same object. So this is like the version that I was showing you before. It's got that weird O1 prefix and all this stuff. So we've moved on in time. An O2 version of that is we've cleaned up all of the naming and we've added a couple of things to it, right? And we want to know what the differences are between O1 and O2. And not just sort of the prefix names and things like that. Semantically, what new information is in O2 that is not in O1? Like, how is the shape of O2 different? And again, we can do that using that gather fields function that I made that just uses field pairs on the inside. And all we're doing here is cleaning up messy data. So I'm taking those field names, I'm stripping the O1, I'm stripping the user, I'm stripping the underscore, and this is just like cleaning up messy data that you would get from any other source, except it is your types. And this is what I mean by, about being able to sort of roll with sort of dirty data, is you should be able to clean all this stuff up for yourself. So here are the cleaned up fields. So O1 user underscore ID is just ID, and we've cleaned up IDs to just IDs, and like user underscore address to just address. Right? So now we have some data that we can compare. So now we gather fields of the other type, O2. And figuring out what's different and what's the same is just using your standard set library that comes with the standard library of Nim. So it's just taking O1, converting it to a set, and finding the intersection of that set with this set O2. And again, the intersection of the set O2 with the set O1. So what this is telling you is that there's nothing in O1 that is not in O2. But inside of O2, there is an email field of type string that is added. And I think that this is hugely important for things like data type migration. We should be able to migrate data types the same way we migrate databases, database columns, and things like that. It shouldn't be all that different, right? And this kind of approach it's testable. You can generate a type based on that migration and see if it works. And it's also human testable. Like a person can go look at that and see what's different. And I think this is like crucial to being able to go from an old version of a type to a new version of a type. Especially if, what we did at work is we had the customer have an old version of this like type, and now we have this new version. We have to figure out how to migrate between the two. It's a hard problem, but being able to introspect in your static environment makes that not so hard of a problem, in my opinion. So next I want to talk about compile time JSON parsing. This is the idea that if you have a sample piece of JSON, from some web servers, from some documentation, whatever, you can convert that to a type using introspection, and then use that type to parse real JSON, right? So here's what I mean. So I have the sample data right here. This is some data that I got from a web service. It's got an ID field, an age field, a grades field. So presumably this is some kind of student. And this is the sort of the shape of the JSON that I need to be able to parse in order to consume data from this web service. So now I can parse it into Nim, and I can do this at compile time. That's what this compile time pragma is. But I'm using the same. This percentage star like function is in the Nim standard library, and it just takes a blob of JSON and parses it into a Nim type, and not into a Nim type, into a Nim representation of that. So this is standard stuff. Like nothing here I'm showing you yet is all that interesting. Any programming language can take JSON, parse it into an internal representation, and we've been able to do this for decades, right? But now I've written a Nim macro that can take that representation of JSON and convert it into a Nim record. Again, this is not really all that interesting. Converting between from a JSON representation into a map of some sort in your native programming language is really not that hard. Again, I haven't shown you anything that's all that interesting, except that now we have this real Nim type that we can work with, and this real Nim value that we can work with. The magic and the magic is really happening when at compile time I have access to the Nim type checker, right? So I can take this value that I just created and say, hey, Nim type checker, what is the type of that value? Tell me what it is at this point in time. And at compile time, it'll infer the value for you. So it'll take that tuple and say, okay, I think the ID is a string, the age is an int, the street is a string, and the grades are a sequence of integers. So now we have a type that we can work with. And the next, and so let's take stock for a second. What have we done here? In a couple of lines, we've gone from sample data to a type, right? And so now we can use that to parse real data, right? So let's say this is real data. So the reason you know this is real data is because there's no compile time pragma here. Assume that we've read this in from some web service, like it's got an ID field and it's got these dashes in it and age of 25, all this other stuff, right? So now Nim provides this macro called to, which takes real data and a type. We can just pass in that type that we inferred from the sample data and use that to parse that real data into a Nim specific structure in a type safe way. And by the way, all of this stuff catches things that are pretty easy to miss. So let's say that grades field had not just a couple of integers in it, but like 200. Like let's say that's the sample data that you have, right? And like the integer 179 was 33.3. That means that all of these things are supposed to be floats, except you wouldn't have known that unless you caught that. But the type checker catches that, right? And it infers a sequence of floats as opposed to a sequence of integers. So the computer's doing work for us. We don't have to go manually like inspect the stuff and then say, oh yeah, that's got to be a float. That is a mistake that you just won't make because the type checker is doing work for you. So what we've done effectively is we've approximated F# JSON type providers in a few lines. And more than that, we can now generate a type from not just a single sample, but a composite of samples. Right, so assume that you didn't have just that one sample data. Assume you had 10 pieces of sample data. And sample data number 9, the grades field was null. What that means then is that grades is now an optional field if you put all that stuff together. You wouldn't have known that. It would have been hard to inspect manually. And you're letting the computer do that work for you. You can generate API reports pretty easily. You can communicate with your front-end team better. Where I work, we have separate back-end and front-end teams. And a lot of times what'll happen is, the front-end team will have a JSON blob that they're working with, and it's not working correctly. So they come back to you and they say, hey, this key, what is that mapped to in your types, like on your back-end? And that is a surprisingly tedious and awkward question to answer in the moment, because it takes a lot of digging around modules and trying to find where the source is that like marshals that JSON into some kind of type, and then trying to figure out what that type is and all of that stuff. And it takes a while. Here you can do it relatively quickly, like in the order of seconds. So what this kind of thing does is it eliminates all of these time-consuming, error-prone things that you do manually, right? But it doesn't take away any control either. So if I wanted to parse that ID as a social security number because I know that's what it's supposed to be, I can do that. That's not a problem. So the last example I wanted to talk about is this idea of using introspection to write a type-safe printf, right? So printf is just sort of there. It's not really about writing a type-safe printf. It's about saying, hey, given some kind of string DSL, can you provide like some kind of type safety around that, compile time safety? So here is a wrong printf, right? So I have printf here. I want to print out some string and some number. But I'm passing things in the wrong order. So instead of passing a string and a number, I'm passing in first a number and then a string. In Nim, I can get this to generate the error. At compile time, argument of type int cannot be used with a format specifier %s. And printf is not anything that comes with Nim. I wrote printf, right? So like I wrote it just for this talk. And it's all just compile time evaluation, macros, and static introspection. And the code for this talk will be available on GitHub, but you can see it's not even that long or even really that interesting. It's not like super clever code or anything. It's just a standard printf. And at the heart of this printf macro is this switch statement, a case statement that says, hey, if you see the format specifier %d, and if the argument you pass in is an integer, then convert that integer to a string, otherwise error out. Now the real magic is happening here in that arg_is. So arg_is is somehow able to introspect on the type of the thing that's being passed in. And arg_is looks like this. It's really ugly. So don't get caught up in this. It's a template that takes a type and does all kinds of stuff. But the real essence of it is right here. So it's getting the type. Get type is a Nim primitive, right? It's provided by the Nim compiler. It says get the type of the argument, get the type that you think it should be, and are they equal? So you're passing an int. It's saying, hey, is this argument an int? If not, it's false. This bool will be false. And I also wrote the error. The error is not something that came built into the Nim compiler. I wrote this template. It's like, I don't know, 5 or 6 lines. Again, a lot of verbosity here, but the essence of it is an argument of type whatever cannot be used with a format specifier whatever. And this matches the type error. So I'm able to use the static environment to generate custom type errors for this printf. And it's not even just providing type errors now. Once you have this level of flexibility, you don't just provide errors when the user does something wrong, you can provide the user help. So I added this format specifier called %_, which is just a wildcard, which says, hey, inspect the argument that you're being passed in and tell me what format specifier I need to be using. So I have printf, some string, some number, and a string. So here I've forgotten what the format specifier for a string is. So for a string, it's not that hard. So you might think this is a contrived example, but I can never remember printf format specifiers. It's like, I don't know, like pointers, longs, unsigned characters, like they all have different ones. And it's really hard to remember all this stuff. And it would be really useful if I could have just, pop it in and have the compiler tell me what it is. And here there's a type error. Well, it's an error. It really should be a warning. It's an error that says try %s. Right. So it's taking it's seeing that that's a string and it's saying, okay, this is the format specifier that you probably want. And the way I did that is just adding one more thing to the bottom of that switch statement. It says that if the format specifier is %_, and if the argument that's being passed in is a string, print out that help message with a %s. If it's been passed in with an integer, print out that help message with a %d. And you could just keep going with this, right? You just add, as many format specifiers as you want with some help. So what I think this does, I think this is a hugely important thing because it closes this feedback loop between the computer and the user. The computer is helping the user, and then the user is telling things to the computer. So it's not just that the computer is reacting when it gets input that it's not prepared for. It is helping the user, and it's allowing the user to help themselves by providing customized error messages and wildcards and holes and things like that. So it's allowing you to have domain-specific DSLs with a domain-specific user experience. That last bit is key, because in type functional programming languages, you can create DSLs all day long. You can create interpreters. You can create interpreters that interpret those interpreters in various contexts and all of this stuff. But the compiler diagnostics you get back at the end of the day don't know anything about those things. And they always look like, the compiler error messages are completely meaningless at that point, except to point to, sort of a source location or whatever, because they don't have access. We don't have a way of, providing that domain-specific user experience. And also, it really bugs the heck out of me when I have something like printf. I know that the compiler, the computer in front of me, knows what the format specifier is supposed to be, but I have to Google for it. Why? Why introduce a third party? Why even read the documentation? All the information is there. The computer should just be able to tell me. I shouldn't have to read the docs to find out all that stuff. And I think that static introspection allows me to do that. So in conclusion, static introspection has problems, but it's definitely worth exploring, in my personal opinion. There's a need for type level reflection because it allows you to have domain specific string formats with domain specific errors. It allows you to query your code base and give you better and more flexible software. Like I said before, one of the biggest things that allows you to do is deal with dirty data at the type level. And we get that. It's not always clean. And we have to be able to just kind of roll with it. And that's my talk. Thank you very much. And I'll take any questions.
Thank you, Aditya. We have some questions on our YouTube Live and on Zoom. I will start with one from YouTube Live. It says from Franco Battaglia about JSON deserializing. Could schemas or data types be defined directly through samples, simplifying documentation a lot, or even generating CRUD APIs based on JSON examples?
Yes, I think so.
Okay. Do you want to add to that, or should I go to the next question?
Well, I mean, so let's see here. So I guess the question is I think the question is, given the sample, could you generate database columns and things like that? Is that the question? I guess we can't.
I will have to ask Franco, but
no,
I think.
Yeah, so if that is the question, I think that you can do that. You can generate the types. You can generate in sort of an ORM query from this, if that's what you mean.
Okay, great. And the next question from Ezequiel Biderman is, which efforts to provide static introspection to functional languages do you know of? And I would add my own question, which is, have you ever thought of doing it yourself, like to do a PR for Nim or something like that?
Well, as far as I can tell, the only functional language that is approaching sort of static introspection is probably Scala. Now that I think about it, I think there's a lot of static introspection stuff currently in Scala. And have I ever thought about it? I have thought about creating my own functional programming language with static introspection. I'm not going to lie about that, but I don't usually venture into creating languages because I don't have much time for it, honestly. But yes, I've definitely thought about that.
It's the dream come true, right? To create your own language.
Yeah, it's just so much time and effort, and it's just me, right? I just don't have the time right now.
Sure, and I would like to ask you as well about what do you see for the future of Nim?
The future of Nim.
We can do a bit of futurology.
Okay. I would really like it to take off because it is currently my favorite imperative programming language. I think that Nim has a great future as a glue language for C and C++ interop between, say, like C++ and another programming language, because Nim can sort of Nim can introspect on the C++ side using something like libclang, and it can also introspect on itself and generate like external like types for different programming languages. So I see a lot of like future there. That is just one possible thing. I know that there's a big Nim code base that is doing like smart contract type stuff, and I think they're currently the biggest user of Nim at this point. But that's my hopeful future. Yes.
Okay, and so where can people see the code you used for this talk and maybe try to implement it at home?
It's not up yet. It will be up in the next half hour or so. Well, yeah, let me work on that.
So your user on GitHub is Deech, just
It
like
is?
Twitter?
Yes.
Okay, so DEECH, right?
Yep.
Okay, so people can use or see the code there in the near future. There's a lot of excitement about it, I think. Let's wait a minute in case there is another question from YouTube Live. And thank you a lot for being here in BuzzConf 2020. And as I say to all of our speakers, sadly we had to cancel the live event, but you are very, very invited to our next live event, hopefully next year in Argentina. So thank you a lot for being here. Okay, and so there's no further questions. So we will go to a break and then our next speaker.
Okay, thank you.
Thank you very much. Okay, so our next talk will be in Spanish. So sorry to our English-speaking audience, but this time we weren't able to have a live translation. So hopefully in the future we will have some kind of subtitles. So I'm going to present next talk in Spanish. Bueno, entonces pasamos al castellano para nuestros televidentes en Argentina y en otros países hispanohablantes. Nuestra siguiente charla va a ser entonces en español por Sergio Chouhy, que es un doctor en matemática, egresado de la UBA y doctorado en la Universidad de Montpellier y la Universidad de Buenos Aires. Trabajó en CONICET, en la Universidad Nacional de San Martín, en la Universidad de Stuttgart y actualmente trabaja en la industria, sí, pasó de la academia a la industria, en una cooperativa de software llamada ERIX. Su charla va a ser sobre implementar Deep Q Learning con PyTorch. Así que le damos la bienvenida a Sergio. Sergio, ¿andás por ahí?
Hola, ¿cómo están?
Hola, ¿cómo estás? Bueno, ya es todo tuyo entonces el control de la pantalla. Cuando quieras puedes empezar a compartir.
Bien, a ver ahí. ¿Ahí se ve?
Perfecto.
Bien. Ahí está. Bueno, primero, muchas gracias quería agradecer a ustedes los organizadores por darme este espacio para dar esta charla, que va a ser sobre una implementación de Deep Q Learning usando PyTorch. Entonces, primero unas palabras sobre qué es Reinforcement Learning. Reinforcement Learning es un área que lo que hace son algoritmos que lo que logran son agentes que aprenden a resolver tareas sin que uno les tenga que decir exactamente qué es lo que tienen que hacer. Es decir, a diferencia de lo que es aprendizaje supervisado en Machine Learning, uno no le dice exactamente cuáles son las acciones que tienen que tomar ante cada situación, sino que las aprende con un sistema de refuerzos y interactuando con el entorno. Entonces, hace unos años empezaron a tener mucho éxito porque se empezaron a combinar con métodos de redes neuronales y se empezaron a lograr varios hitos que hasta el momento parecían totalmente inalcanzables. Por ejemplo, se logró hacer un programa que le gane al mejor jugador del mundo de Go. Es un juego chino que es muy difícil por la cantidad de estados que tiene y el espacio de acciones es muy grande. Bien, después ya hace un par de años se escaló un poco más y se logró hacer un programa que le gane a los mejores jugadores del mundo de StarCraft, que ya tiene un espacio digamos, de estados muchísimo más grande y el espacio de acciones también es muchísimo más grande. Pero además es un juego en tiempo real, a diferencia del Go, que es por turnos. Y ya el año pasado se sigue escalando porque se logró hacer un programa que le gane a jugadores pro de Dota 2, que además de ser también en tiempo real como el StarCraft, es además cooperativo. Pero bueno, un poco toda esta revolución tiene un poco origen en este paper, en el que los autores lograron combinar técnicas de reinforcement learning con técnicas de redes neuronales para hacer un algoritmo que aprendió a jugar 2.600 juegos de Atari sin ningún tipo de personalización especial para cada juego. Simplemente la gente se expone a un juego y interactuando y con el juego una y otra vez logra aprender cuáles son las acciones que tiene que tomar para poder ganarlo. Bien, y en estos casos digamos, el input del modelo, el input de la gente es la pantalla, la imagen que uno vería si estuviera jugándolo. Bien, así que la charla es un poco una implementación de este algoritmo, siguiendo este esquema, esta arquitectura. Que un poco resume cómo es todo el flujo, ¿no? Hay un entorno, que en este caso va a ser un jueguito, que la gente interactúa con el entorno le dice cuál es el estado, el agente usa ese estado para tomar una acción, se le informa al entorno, y el entorno tiene toda una lógica interna de cómo evoluciona, y le vuelve a informar un estado, y así, ¿no? Es un ciclo hasta que termina el episodio, que sería cuando uno pierde o gana en un jueguito. Y simultáneamente, mientras eso va sucediendo, se van guardando los estados, las acciones, las recompensas, el estado al que se llegó y una variable que dice si el episodio terminó o no. Todas esas transiciones se van guardando en un dataset que después es usado por el algoritmo que, digamos, es donde está la parte de la inteligencia. Este learner esta cajita es un algoritmo que consume de esas experiencias pasadas y modifica la forma de accionar de la gente, ¿no? Entonces todo eso sucede en simultáneo y la gente entonces va, digamos, aprendiendo a resolver el problema con el que está interactuando. Bien. Entonces, para mostrar un poco rápido a dónde quiero llegar, es este código de acá, va a ser, digamos, representa todo este flujo de acá, ¿no? Una vez que definamos todas estas clases, cada clase va a corresponder a una cajita en este diagrama, y bueno, vamos a tener un bucle, un for loop, en donde que recorre 350 episodios, y acá se ve como el agente recibe el estado, toma una acción, se le informa al entorno, el entorno tiene toda su lógica interna que hace que las cosas, digamos, evolucionen, informa cuál es el próximo estado, cuál fue la recompensa, si se terminó, y alguna otra información. Todo eso se guarda en el dataset, Y después el learner se actualiza digamos, la función que toma las decisiones en el agente. Bueno, entonces voy a ir cajita por cajita una de estas mostrando la implementación. Entonces, empecemos por el entorno. El entorno lo vamos a sacar de Gym, que es una librería de OpenAI, que bueno, nos regala esta parte del funcionamiento de la lógica interna de cómo funcionan. El ejemplo que voy a tomar es este de Cartpole, que el objetivo es mover el carrito para balancear el poste. Entonces es muy fácil instanciar estos entornos. Hay que importar Gym simplemente y hacer gym.make, y eso ya nos da el entorno. Entonces le podemos preguntar, por ejemplo, cuál es el espacio de acciones. Acá discrete de 2 significa que hay 2 acciones posibles. Le podemos pedir que nos diga una al azar, pidiendo una muestra, y acá nos devolvió 1. Las 2 opciones son 0 o 1, que corresponden a la izquierda o derecha. También le podemos preguntar cuál es el espacio de estados posibles, que nos dice box 4. Eso significa que son tiras, son tuplas de 4 coordenadas con valores reales, digamos. Y después tenemos siempre la posibilidad de resetear, de traer un nuevo episodio reseteando el entorno. Y cada vez que hacemos eso, eso nos da el estado inicial. Que como ven acá, son 4 números que corresponden a la posición, la velocidad del carrito, el ángulo y la velocidad angular. Bien. Tiene una función render también, que lo que hace es imprimir, abrir una ventanita con este dibujito. Y si nosotros quisiéramos interactuar con el entorno, tenemos un método step, a que le pasamos alguna de las 2 acciones posibles, que son 0 o 1, y esto nos devuelve 4 cosas. Nos devuelve la nueva observación, toda la lógica interna, toda la física del juego evoluciona y te dice, ok, la nueva observación es esta, la recompensa que obtuviste es esta, 1. Esto es una variable que dice si terminó o no el episodio, y eso es información extra que en este caso en particular, para este entorno, es siempre vacía. En ese entorno nos dan recompensa siempre 1, el episodio termina cuando el poste supera cierto ángulo. Entonces la manera de conseguir más recompensa es tratando de sobrevivir el mayor tiempo posible. Bien, entonces lo primero que podemos hacer es jugar acá o interactuar con acciones aleatorias. Entonces, esto sería como lo más básico que uno puede hacer, es tomar una acción cualquiera, acá no hay ningún agente interactuando con nada, uno le pide una acción aleatoria y se la enchufa al entorno y vemos qué es lo que haría un agente que toma decisiones aleatorias. Para digamos, ver qué sucede, uno tiene estas funciones de Gym, y es simplemente esto, nos devuelve una ventanita con este videito acá que se está repitiendo muchas veces, ¿no? Pero lo que sucede es que toma acciones aleatorias de ir para la izquierda y para la derecha, y finalmente se le cae el palo y termina. Bien. Entonces, si repetimos esto 350 veces, y en cada uno de estos episodios vamos acumulando todas las recompensas, que eran siempre 1, es decir, vamos calculando cuánto tiempo pudo balancear el poste, eso nos da este gráfico que está acá abajo, que, como verán, hay veces que tiene suerte y logra mantenerlo bastante tiempo, y hay veces que tiene mala suerte y no, pero tiene un comportamiento así inestable, y esto es lo que uno puede esperar de algo aleatorio. Entonces, la primera intervención que vamos a hacer es tratar de enchufarle un agente, ¿no? Entonces, eso simplemente se va a traducir en reemplazar esta línea que está acá por una línea en la que tenga esta pinta de acá arriba a la derecha, ¿no? Vamos a tener un objeto agente que tenga un método al que uno le pasa un estado y devuelve una acción. Con suerte que tenga sentido, ¿no? Entonces, eso nos dejaría en esta parte del diagramita. Vamos a tener un agente que da una acción, se la informa al episodio, al entorno, el entorno evoluciona con su lógica interna y después le devuelve el nuevo estado, y así hasta que termina. Bien, entonces veamos la implementación del agente. El agente lo único que tiene que tener es un método, como dije antes, select action. Entonces, lo que va a hacer el agente va a ser un usuario de una función policy que le va a dar una probabilidad de cuál es la acción más más probable de que sea la mejor, ¿no? La más prometedora. Por ejemplo, va a dar un par de números que están entre 0 y 1 y sumen 1. El de la izquierda va a ser la probabilidad de elegir la acción de la izquierda y la probabilidad de elegir la acción de la derecha. Entonces, el agente va a ser así de simple, va a ser una clasecita que le vamos a dar la policy, que ahora vamos a ver qué es, y la va a usar, le va a pedir cada vez que viene un estado, le va a decir, ok, dame la distribución esta de las probabilidades de las acciones más prometedoras, y voy a hacer algo. En este caso, lo que está haciendo es quedándose con la acción que tiene mejor probabilidad. Pero bueno, eso es una decisión de esta implementación, no podría ser otra cosa como, por ejemplo, tomar una acción sampleada con la probabilidad que es la distribución, ¿no? Por ejemplo, el 30% de las veces elegimos la acción 0 y el 70% de las veces la acción 1 para este estado en particular. Y hay que complicarlo un poquitito más, pero no mucho esto, porque la policy esta va a ser la parte que, digamos, aprende, ¿no? El learner, el algoritmo que toma las interacciones pasadas, experiencias, y actualiza la policy. Y al principio la policy va a ser algo que no tenga sentido. Y uno podría tener mala suerte y en ese momento en el que la policy no tiene sentido, que, por ejemplo, elija siempre la acción de la izquierda o siempre la acción de la derecha. Y si eso sucede, el agente nunca va a elegir la otra acción, entonces nunca se va a exponer a ese resultado y no va a poder aprender de eso. Entonces lo que se hace siempre es agregarle algún grado de aleatoriedad. Entonces en este caso le pasamos un parámetro epsilon y que va a ser la probabilidad de tomar una acción aleatoria. Entonces si con esa probabilidad vamos a elegir una acción aleatoria entre 0 y 1, y si no, bueno, vamos a tomar la que sea más prometedora. Bien, entonces la policy, vamos con la policy. La policy va a ser esta clase que está acá, y acá es donde aparecen las redes neuronales. Para el que no sabe qué es una red neuronal, en este caso, y muchas veces es simplemente una secuencia de operaciones matriciales compuestas con operaciones no lineales. Por ejemplo, en este caso es bastante simple, lo que va a hacer este modelo que está acá es, cuando venga un estado, que va a ser una va a ser una tupla con cuatro coordenadas, se va a multiplicar primero por una matriz de 50 por 4, acá state dimension va a ser 4, lo que va a resultar en un vector de dimensión 50, y esto se va a ir ejecutando secuencialmente, ¿no? Después ese vector de dimensión 50, de 50 coordenadas, va a pasar por esta capa, que lo que hace es fijarse todas las coordenadas que son negativas y reemplazarlas por 0, y las otras las deja igual. Y el resultado de eso va a pasar por una matriz de 50 por 2, que va a devolver un vector de 2 coordenadas, que el objetivo es que ese vector de 2 coordenadas sea, por ejemplo, la esperanza o cuánto se espera que uno puede conseguir, cuánto recompensa uno puede conseguir a partir de ese momento si toma las mejores decisiones. Pero bueno, esto al principio va a estar PyTorch. Esta es la parte Torch. Esto es PyTorch, ¿no? Para usar esto hay que importar PyTorch, que simplemente es import torch. Y cuando uno instancia un modelo así, viene con entradas aleatorias. Estas matrices al principio no tienen ningún sentido en particular para el problema este, ¿no? Pero bueno, entonces, acá está este método getDistribution, que primero tiene que convertir el estado a un tensor de PyTorch, que es el equivalente al NumPy array, evaluar el modelo en ese estado, eso da unos valores, y después la distribución la consigue usando esta función softmax, que lo que hace es normalizar ese vector para que las coordenadas estén todas entre 0 y 1 y sumen 1. Y después esta parte de acá, que parece complicada, es algo de PyTorch, que hay que pedirle la data, son los valores de la distribución, extraerlos del tensor, pasarlos de las memorias potencialmente que estén en el GPU, pasarlos al CPU, y después convertirlo en un array de NumPy. Bien, para que esto esté mejor implementado hay que hacerle un pequeño cambio, que es agregarle este bloque, que lo que le dice es, ok, acá no voy a querer calcular ninguna derivada. PyTorch por defecto asume que siempre uno quiere calcular derivadas, cuando apenas uno empieza a hacer operaciones, empieza a calcular un grafo con todas las operaciones que uno va haciendo para rastrear después y poder calcular las derivas parciales. acá no lo vamos a necesitar porque acá esta no es la parte de la optimización del modelo, así que con esto le decimos a Python, ok, acá no vamos a calcular derivadas, no te gastes en calcular este grafo. Y después está esta línea de model.eval, que en este caso no hace nada porque todas las capas de nuestra red neuronal tienen comportamiento igual en entrenamiento y evaluación, pero hay capas que son distintos los comportamientos, como por ejemplo si uno tiene dropout o batch, ¿no? Pero bueno, mejor que esté ahí. Ya, si uno después se olvida y cambia alguna capa, es importante que eso esté ahí. Bien. Entonces, ahora ya podemos ir enchufando nuestro agente y nuestra policy en lo que era el flujo de antes. Y bien, entonces los instanciamos primero. Y la acción ahora, en vez de ser aleatorias, va a ser lo que decida la gente en función de la policy, ¿no? La policy en principio, al principio no va a tener ningún sentido en particular y esto no va a andar bien. Entonces eso lo podemos ver. Podemos hacer lo mismo que antes y tomar una acción que sea con los pesos de la matriz de la red neuronal que vienen por defecto, y uno de cada 10 veces vamos a tomar una acción aleatoria. Entonces, si ponemos esto a correr y rastreamos cuáles son las recompensas acumuladas en cada episodio, es decir, cuánto tiempo logra balancear el poste, eso da esto que está acá abajo, que es peor que, por ahora es peor que lo aleatorio, ¿no? 8 es lo mínimo, 16 es lo máximo cuando tuvo un poquito de suerte, y eso porque, bueno, tiene muy poca aleatoriedad y siempre está tomando decisiones que son malas. Bien, entonces, ahora vamos con la parte que va a usar estas experiencias que está acumulando, que bueno, todavía no se acumulan, ¿no? Pero va a usar estas experiencias para acumularlas y después aprender. Entonces, nosotros estamos parados acá ahora y lo que vamos a hacer es completar con estas dos cajitas. Entonces primero vamos a tener una cajita que es el dataset, que se guarda todas las interacciones, y después vamos a tener otra capa, otra cajita que es learner, que va a estar el algoritmo que usa esas experiencias para modificar los pesos de la red neuronal. Bien, entonces vamos primero con el dataset, que es más simple. Entonces el dataset va a ser esta clase de acá, va a ser simplemente una cola FIFO. Va a tener su memoria y va a tener dos métodos, uno push para darle transiciones, y va a tener este otro método para pedirle muestras aleatorias, ¿no? Vamos a decir, ok, ahora dame, de todas las interacciones, dame 16 muestras aleatorias. Bien. Entonces, eso lo podemos ya ir agregando a ese código que teníamos. Entonces ahora, además de la policy y el agent, vamos a tener el dataset, ¿no? Que lo instanciamos así, y ahora vamos a tener que hacer un pequeño cambio, porque antes estábamos todo el tiempo pisando el estado con el siguiente estado. Ahora vamos a, por un momento, mantener los dos para poder pasarle al dataset esta transición. La transición es el estado en el que se estaba, la acción que se tomó, la recompensa que se obtuvo, el siguiente estado, y si el episodio terminó o no. Y bueno, después sí pisamos el estado con el siguiente estado para que la gente reciba información actualizada, ¿no? Bien. Y ahora vamos con el learner. El learner, bien, el objetivo del learner va a ser poder modificar los pesos de la policy, de la red neuronal, para que eso empiece a tener sentido. Entonces, para explicar un poco cómo va a funcionar eso, es cómodo introducir un poco de notación. Entonces, este model que me refiero acá es la red neuronal, va a ser el model de la policy. Y vamos a usar esta notación, que es la primera coordenada la vamos a llamar q de state, 0, y la segunda coordenada la vamos a llamar q de state, 1. Entonces, idealmente lo que vamos a querer, el objetivo, o sea, si pudiéramos elegir lo que queremos, sería conseguir esto, que q de state, 0 sea lo máximo que uno puede conseguir tomando las mejores decisiones a partir del momento en el que se está, ¿no? A partir de este estado, si yo tomo las mejores decisiones, ¿cuánto puedo sobrevivir? Y lo mismo para q de state, 1, ¿no? Esta función q es una función importante de reinforcement learning, digamos, tiene su historia, siempre se escribe Q, y digamos, el algoritmo se llama Deep Q-Learning por esta Q, ¿no? Bien. Entonces, escrita de esta manera, uno puede empezar a jugar un poco, y unas cosas que se obtienen es esta ecuación de Bellman, que lo que dice es, o sea, ya directamente por la definición de esta Q así como está, si estamos en un estado y tomamos una acción, y el siguiente estado es el último, entonces lo máximo que podemos conseguir a partir de ahí, obviamente va a ser esa recompensa inmediata. Y si no, va a ser esa recompensa inmediata más lo máximo que podemos obtener a partir de ese próximo estado. Entonces esto ya lo que nos da esta ecuación de Bellman, que es súper importante en Reinforcement Learning, y la vamos a usar para modificar los pesos de la policy usando el método del gradiente. Entonces para eso vamos a pasar restando esos dos términos, y los vamos a elevar al cuadrado para tener una función que minimizar, ¿no? Si la elevamos al cuadrado y la minimizamos, logramos que esos dos términos de la derecha y de la izquierda de esta igualdad sean iguales. Bien, entonces, resumiendo un poco eso, lo que tenemos es que tenemos este modelo que era el de la policy, y lo queremos optimizar para que tenga sentido las decisiones. Y eso lo vamos a hacer minimizando esta función, exactamente esta que está acá. Entonces, ¿cómo se ve eso en el código? Bueno, para una transición es esto que está acá, ¿no? Entonces, nosotros tenemos nuestro dataset que tiene sus experiencias, tiene experiencias pasadas guardadas. Le podemos pedir una muestra de una transición. Y, bueno, primero, como todo, hay que convertir los tipos de NumPy array, que es lo que nos da Jim, a tensores de PyTorch, que es lo que necesitamos para poder evaluar los modelos de PyTorch. Y después, bueno, esta Q que está acá va a ser la policy, el modelo de la policy evaluado en el estado y en la acción, es decir, el Q de state, que es esta Q que está acá a la izquierda. Y después estos next values van a ser Q de next values. Bien, y simplemente eso, no hay mucha más vuelta que darle. La loss va a ser, si terminó el episodio, vamos a hacer simplemente Q menos reward al cuadrado, y si no terminó, vamos a hacer Q menos reward menos next value, el máximo de los next values, que es exactamente esta fórmula que está acá. El problema con hacerlo transición por transición es que puede llegar a haber transiciones confusas, y esto se va a volver inestable. Entonces, lo que se suele hacer en Deep Learning es esta idea de tomar mini batches. Entonces, en vez de tomar una transición, vamos a tomar un conjunto de transiciones aleatorias, y vamos a calcular para cada una de esas transiciones este número loss, y lo que vamos a usar para el método gradiente es el promedio de esos. Bien, entonces, ¿cómo se ve eso en el código? Bien. Entonces, esta es la clase learner, que le vamos a dar una policy y un batch size, y va a ser exactamente eso que dije antes, pero para batch size muestras aleatorias al mismo tiempo. Entonces, eso lo que va a hacer es apilarlas, todos los estados, cada estado tiene dimensión 4, entonces los va a apilar en una matriz de 4 por batch size, que va a ser 16, y eso se lo vamos a dar al modelo para que haga todas las cuentas al mismo tiempo. Entonces, en el código extraemos el mini batch, desempacamos los estados, acciones, los rewards, los próximos estados, y todas las variables que dicen si terminó o no terminó el episodio en ese momento. Los convertimos a tensores de PyTorch. Acá hay que además convertir los rewards y las acciones porque ya dejan de ser números, y uno necesita tratarlos como tensores para que PyTorch haga todo el broadcasting. Y después esta que está acá es la misma que estaba antes, pero haciendo todas las cuentas en simultáneo. Entonces calculamos los valores Q. Este gather lo que hace es, estos values ahora va a ser una matriz con dos valores, el Q0 y el Q1 para cada uno de los estados, y gather lo que hace es, se queda con la columna correspondiente a la acción que se tomó en esa transición. Y después, acá no está ese if que estaba antes, porque está codificado en esta multiplicación que está acá, que lo que hace exactamente eso, ¿no? Cuando el episodio terminó, todo este valor es 0, entonces se multiplica por todo esto, y lo único que queda es rewards. Y cuando no terminó, bueno, esto da 1 y multiplicado no da nada, ¿no? Y después la loss va a ser simplemente la resta al cuadrado promediado. Acá hay un detalle, bueno, y después está esta parte que es la forma de hacer el método del gradiente con PyTorch, ¿no? Limpia todos los residuos que hayan quedado de alguna otra corrida, calcula las derivadas parciales y hace el método del gradiente. Hay un detalle que es que en el paper original mantienen una copia del modelo, porque esto que está acá, para este caso en particular de carpool, no hace falta, pero para otros entornos esto puede ser inestable. Entonces, lo que se hace es mantener una copia de la policy para calcular esta parte que está acá, para calcular la parte de los next values. Esta policy que está acá, normalmente se hace con una versión vieja de la policy que cada tantos pasos, cada tantas interacciones se sincronizan. Entonces, como normalmente se usa una policy vieja, esa policy no es la que se está derivando y la parte del targets, las derivadas siempre dan 0. Entonces, en este caso que estamos usando la misma, le tenemos que decir a PyTorch que las derivadas de target sean 0. Entonces, eso se lo decimos con target.detach. Bien, y eso es prácticamente todo el código. Lo podemos volver a ver acá. Entonces, instanciamos el entorno, instanciamos la policy, se la pasamos a la gente, instanciamos el dataset y el learner, que le damos la policy y le decimos un batch size de 16, es decir, va a calcular en cada momento, va a calcular la loss para 16 muestras. Y esto se lo enchufamos a este for loop, que él corre por 350 episodios y hace esto, ¿no? La gente toma una acción, el entorno reacciona, con su lógica interna nos dice cuál es el próximo estado, el reward y demás. Se lo damos al dataset, después el learner le pide al dataset, ok, dame 16 transiciones pasadas, y después usa eso con el algoritmo que vimos recién para actualizar la policy. Y bueno, esto va sucediendo y la gente va aprendiendo. Entonces, eso es lo que se ve acá. Que se ve que al principio anda muy mal, como se veía en el anterior gráfico, que estaba siempre entre 8 y 16 como mucho. Y en algún momento empieza a juntar suficientes transiciones como para empezar a aprender y se empieza a despegar. Se empieza a despegar y empieza a aprender cada vez más y cada vez más hasta que logra resolver el problema. Y acá están un poco las transiciones en el momento, ¿no? En el momento del episodio 5 todavía no hacía nada razonable. En el episodio 75 ya se empezó a dar cuenta un poco que tenía que correrse para la izquierda, se le empezaba a caer el palito. En el episodio 120 la verdad que mucho más no avanzó, pero duraba un poquito más. En el 150 ya la empezaba a tener más clara, y abajo a la izquierda pueden ver que el resultado final, que es que nada, lo mantiene ahí, lo mantiene balanceado. 200 es el máximo porque, 200 es el máximo porque el episodio termina o cuando se le cae el palito o cuando llega a 200, ¿no? Hay una versión 1 que del carpool, es el carpool B0, hay una versión 1 que lo que te dice es, bueno, tenés hasta 500, entonces uno tiene un poco más de margen para seguir entrenando. Y después, este mismo entorno, uno se lo puede enchufar al Swing Up Carpool, que es otro entorno parecido, pero en donde la gente tiene que además aprender a levantar el palito. Es un poco más divertido, y lo que sucede arriba ese es un caso, es un mínimo local, porque en este caso lo que le di fue, la recompensa en este caso era 1 si el ángulo estaba por encima o sea, si lo mantenía por arriba, y 0 si no. Entonces, arriba lo que aprendió es una estrategia, digamos, subóptima, pero que le funcionaba bastante, que es agitar el carrito para que el poste ese esté cada tanto por encima del eje X. Bien, hasta acá llega esto. Solamente queríamos mencionar también un par de ejemplos que me gustan de Deep Reinforcement Learning en la industria. Y son estos dos porque esto va más allá de juegos y robótica y demás. Estos son dos ejemplos en donde el problema que se resuelve no tiene en principio que ver con controlar algo que una persona podría controlar. Y es que Facebook tiene estos algoritmos funcionando para enviar notificaciones, las notificaciones que uno recibe en el celular de actualizaciones y demás, las maneja un agente que lo decide o no en función de tratar de maximizar digamos, que uno, no solamente en hacer clic en esa recomendación o esa actualización en particular, sino tratar de maximizar el compromiso a largo plazo. Y después Zynga es una empresa que tiene videojuegos y esta empresa está usando Reinforcement Learning, Deep Reinforcement Learning, no solo para hacer recomendaciones de sus juegos o para mandar recordatorios de jugar tal o cual juego, sino que además está usándolo para personalizar directamente los juegos, ¿no? La dificultad de los juegos la decide un agente para tratar de que a uno le sea más divertido, y después directamente los niveles en sí también los está personalizando usando estos algoritmos. Pero bueno, muchas gracias por escucharme. Hasta acá llegó.
Bueno, muchas gracias a vos, Sergio. Y yo te quería preguntar, además de estos usos que mencionás en la industria, si has tenido la oportunidad de aplicar en algún momento Deep Q Learning y cómo llegaste al paper también.
En ERIX siempre los consideramos, y hay un par de proyectos en donde estamos indagando y viendo si tiene sentido. ¿Y cómo llegué al paper? Yo lo primero que me crucé fue con la noticia en el 2018 de que había un programa que le ganaba a los mejores jugadores de StarCraft. Y de ahí, a partir de ahí empecé un poco a leer al respecto.
Bien, buenísimo. Acá hay una pregunta de Iván Mindlin. Dice, ¿la complejidad aumenta solamente por la cantidad de acciones o puede incluir el tipo de acción?
También el tipo de acción. Esto que yo conté es para acciones discretas, cuando son acciones continuas, como en el caso de StarCraft, o cuando uno tiene que... Sí, cuando la acción es continua, ya ahí son otros métodos que son un poco más complicados. Pero sí, también la dificultad puede ir por otros lados. Por ejemplo, si tu recompensa es ganar un juego y el juego es muy largo y requiere muchísima exploración, la dificultad también puede venir por ese lado.
Claro. Y comentabas recién como, bueno, ustedes están evaluando usar este tipo de tecnologías para algunos proyectos. ¿Qué cosas toman en consideración para evaluar si tiene sentido o no?
Bueno, primero que, digamos, la acción que uno toma, que en un sentido es una predicción, influya en el estado que uno el estado que uno está considerando, ¿no? Si la predicción, si las acciones no tienen consecuencias, ya ahí deja de tener sentido. Así que en principio sería eso. Sería, sí, cuando uno quiere, por ejemplo, cuando el objetivo es lograr maximizar algo a largo plazo, en lugar de en el futuro inmediato, ¿no? Eso sí.
Buenísimo. Bueno, acá te llegan felicitaciones de Maya Numerovsky, cuyo apellido me gustaría tener, es muy apto. Así que bueno, muchísimas gracias, Sergio, por estar acá en BuzzConf. ¿Y dónde te puede seguir la gente? ¿Tenés Twitter o dónde pueden leer más sobre el tema?
El código lo voy a subir a mi GitHub, que es ese Chouhy, mi nombre y mi letra inicial del nombre y el apellido. Así que todo esto que les conté lo van a poder encontrar ahí. Todavía no lo subí, pero lo voy a subir pronto.
Perfecto. Bueno, muchísimas gracias y nos despedimos por hoy de la BuzzConf. Seguimos mañana a la misma hora de siempre. Chau, chau.
Chau.